Hello students, this lecture is about Ohm's Law and applying it to series circuits. So we've already learned about Ohm's Law, which is a relationship between voltage, resistance, and current. And we're going to learn how to apply that to specific kinds of circuits. So our objectives in this lesson are to be able to identify a series circuit based on how components are connected in a circuit. And we'll learn some rules for that. And then we'll also learn some rules for applying Ohm's Law to series circuits. Okay, our first step is let's see what a series circuit even is. So a series circuit is a circuit in which the components are lined up one after another in a single path. It's just like a television series or any other sort of series. We have one thing after another after another. So right here I have my battery. There it is, positive side. And current is going to flow through this circuit from positive to negative. It passes first through this resistor, then through this resistor, then through this resistor. It has to go through them one after another, just like a series. We're going to see a different kind of circuit later in this unit called a parallel circuit, where it can go through many different components at the same time. That is not this circuit. So electricity has to go through these components one after another in a single path. That's going to become important. There's only one path for current to flow. And we'll see why that becomes important in a little bit. So some things about series circuits. One, the total resistance of a series circuit, we're going to define that as the sum of all resistances in the circuit. And this word sum comes from Latin. It's also from math. Then it just means to add up all the resistances. So I could say that the total resistance is equal to, first resistance plus the second resistance plus the third resistance, and so on and so forth. If I have multiple resistors in a circuit, I could just add them up to get the total resistance. And that's going to be important when we go to make some calculations on series circuits. The current is the same for all components and depends on the total resistance. So the reason the current is the same is because there is only one path for current to take. If we look back up at a series circuit, there's only one road for current to go from positive to negative. It's got to go through this wire, through the resistor, then through this resistor, then through this resistor, and back over to the negative side of the battery. There's no choice. The current has no other way to go. If we added on, let's say we had a bulb over here on the right hand side, now there are two paths for current to flow. Current could go through this resistor, or it could go over here through that bulb. That is what's called a parallel circuit. We'll do it later. In a series circuit, there is only one path, one loop, to get from positive to negative. Because there's only one path, the current has to be the same, because that is how electricity is flowing. Only one way for it to flow. The voltage is different across each component in a series circuit, and it depends on that component's resistance. And that's easier to explain with an example, so if that doesn't make sense right now, hang on to it. We'll come back to that in a numerical example. But in essence, if I were to take a multimeter and measure the voltage across just that resistor, it may not necessarily be the same as this resistor over here, and that could be different from this resistor over here. So each of those individual voltages could be different. They could be different in a series circuit. Current is the same, but voltage is different. And the total voltage drop must equal the battery voltage. This is a vocab term we learned very early when we started talking about circuits, and we defined current and voltage when we did the electron shuffle in class, and then we also defined something called a voltage drop. The voltage drop is the voltage across any particular component. So I may have a particular voltage here. Let's say this battery is a 24-volt battery, and I could measure the voltage drop from here to here. I could put a voltmeter right there in the circuit, and I could say, all right, I'm going to take my multimeter and measure the voltage drop across just that component. or any other component that I want. And what this statement down here is saying is that the total voltage drop must equal the battery voltage. So if I add up the voltage drops across this resistor, and then took the voltage drop across this resistor, and then this resistor, they all have to add up to whatever the battery's voltage is. And we can visualize this by thinking back to the electron shuffle. In a 24-volt battery, when we did the electron shuffle in class, each individual electron would have 24 cubes of energy, because voltage is the amount of energy per charge, or per electron. So when it goes to the first resistor, it has to give some of its energy to the first resistor, then it has to give some of its energy to the next one, and some of it to the next one in the circuit, and so on. And when it gets back to the negative end of the battery, those electrons were not allowed to have any energy left in their hands. They had to have 0 volts left. So whatever I drop over each of the components better add up to 24. Because I have to get rid of all of that energy. We can see that in a diagram here, which is in your textbook as well. And this diagram is showing how energy flows through a series circuit. In this particular case, we have 3 volts of energy per charge in the circuit. The electrons are marching through. They give 1 volt of energy to this first battery. Then they march to the next one. They march to the next one. Going on down, the total amount of volts that they drop, the voltage drop across each bulb, has to add up to 3 volts. Okay, otherwise these electrons are not going to have empty energy when they get back to the battery, which is part of our rule. So that helps. This defines a series circuit and tells us some things about a series circuit. Let's go on to see how we can use some rules to solve for the currents and voltages in a series circuit. Okay, let's take a look at some rules about how to solve a series circuit. Step 1, generally, we know the resistances of the components in the circuit, whether they're bulbs or they're resistors. In most cases, the resistance of those bulbs is known. So step 1 is to find the total resistance by adding up the resistance of all the components. I take the resistance of the first component, then the second component, the third component, and so on, however many components I have in series, in a row, and then I add them all up. And that's going to give me the total resistance of the circuit. Step number 2. I'm going to find the total current using Ohm's Law for the whole circuit. Now, if you remember, Ohm's Law is I equals V over R. Current equals voltage over resistance. And what I'm specifying here is that you need to find the total current. Total current means current through the whole circuit. So I'm going to put a little TOT there and say that's total current. Is going to equal the total voltage. So usually this is your battery voltage over your total resistance. This total resistance is what you found in step 1. You add up all the resistance of all the components, you get the total resistance. You have this value right here, total resistance. Okay, so then you have battery voltage divided by the total resistance. You're going to find the total current of the circuit. Step number 3, find the voltage drop across each component using Ohm's Law for each individual component. So we do Ohm's Law again. We do I equals V over R, but this time we do it over each individual component. Okay, if that doesn't make sense, let's see an example step by step. Okay, here's an example series circuit. I know it's a series circuit because the components are all right in a row. The electric current is going to have to go from positive to negative, and it's going to have to go through each resistor one after another after another. I'm going to label these resistors. I'm going to say this one is resistor A, and its resistance is, we'll say, 1 ohm. If you recall from Ohm's Law, the units of resistance are ohms. This one over here, I'm going to call it resistor B, and we'll say that's 2 ohms. So it's twice the resistance as resistor A. Twice as hard for electricity to move through that resistor than the first one. And I'm going to call this one resistor C. And we'll say that it is 3 ohms. 3 ohms of resistance. So I have 3 different resistors, all connected to the same battery. And let's say that we have a 12-volt battery here. Okay, 12 volts in the circuit, and those 12 volts, those 12 energy per charge, are being shared by 3 different resistors. Okay, our task: find the total resistance, total current, and the voltage drops across all resistors. Now, step 1 in solving any physics problem is to write my knowns, but as you know, drawing a good physics diagram and labeling that diagram does count as drawing our knowns. So if I draw a proper circuit diagram and I label everything I know on that diagram, this counts as drawing my knowns. I've made myself a little reminder of all the things that I know that's going to help me solve the problem. Other things, I know that I'm going to need to use Ohm's Law. Anytime we have a circuits problem, let's write down Ohm's Law so that we have it for reference. I equals V over R. So step 1, let me go up to my steps. Step 1 is find the total resistance by adding up the resistance of all the components. Step 1, let me add up the resistance of all those components. So R total is going to be RA plus RB plus RC. I have 3 resistors in this circuit. I'm just going to add them all together. This is 1 plus 2 plus 3 equals 6 ohms. That is the total resistance of this circuit. That is how difficult it is for electricity to move through this path. And we only have one path because it's a series circuit. So I've found my total resistance, 6 ohms. Step number 2, find the total current using Ohm's Law for the whole circuit. So what I mean for the whole circuit is I'm looking for total current equals the total voltage over the total resistance. The total voltage of this circuit, if I look back up at my nodes, at my circuit diagram, is 12 volts. That's the battery voltage. So this is 12, and I just found the total resistance of the circuit, and that is 6. So 12 divided by 6 is 2, and units of current is amps, or amperes. Okay, so 2 amps of current through this circuit. Last step, I need to find the voltage drop across each component using Ohm's Law for each individual component. Okay, so that sounds a little bit complicated, but actually what it means is just I'm going to go one at a time through my resistors and zoom in. I'm zooming in right here on resistor A. So let's zoom in on resistor A. So I'm going to put resistor A right here. I know I need to use Ohm's Law on resistor A, so I'm just going to write current through resistor A should equal the voltage drop across resistor A divided by the resistance of resistor A. This is just Ohm's Law, but what I'm saying is I'm zooming in just on component A, on resistor A. Well, I know the current through resistor A. That's known. If we go back to what we know about series circuits, we said that the current is the same for all components and depends on the total resistance. So we found the total current using the total resistance. We found it right here. There it is. And if I find the current anywhere in a series circuit, I've found the current everywhere. Because there's only one path, this 2 amps is the current everywhere in the circuit. Okay? Every component has 2 amps of current moving through it. So the current is 2. I do not know the voltage drop across resistor A. That's what I'm trying to find. But I do know resistor A's resistance. I know that it is 1 ohm. If I solve for the voltage drop across resistor A, I get 2 volts. I just move the 1 to the other side. Okay, voltage across resistor A, 2 volts. Let's look at resistor B. Looking for Ohm's Law, I equals V over R, and this time I'm zoomed in on resistor B. So I'm saying that the current through resistor B should equal the voltage across resistor B divided by the resistance of resistor B. Current through a series circuit is the same through all components. In this case, it's 2 amps. We do not know the voltage across the resistor, but we do know its resistance. We're told in our knowns that it is 2. I go back up here, and we are now zoomed in on this component right here. Resistance of B is 2 ohms. So let's go down. I'm just going to move that to the other side. Voltage across B is 4 volts. And finally, let's zoom in on resistor C. Same thing, Ohm's Law, but zoomed in on resistor C. The current in a series circuit is the same for all components. Once I find the total current, that is the current for all components in the circuit. 2 amps of current is flowing through all components. So that's 2. I don't know the voltage, but I do know its resistance, 3 ohms. I'm going to move that 3 to the other side. So voltage across resistor C is 6 volts. Okay, so we've solved our circuit. We're done with our steps, but let's think about what this physically means. First of all, the voltage across each of these components is not the same. If I took a multimeter and I measured the voltage across this first component, I would only get 2 volts. My multimeter would read 2 volts. And then I'm going to measure across this component. My multimeter would read 4 volts and then 6 volts. But notice, if I added up all of these voltage drops, if I added them up, let's see what the total voltage drop is. So VA plus VB plus VC, 2 plus 4 plus 6 is 12 volts. That number should look familiar because it is in fact the voltage of the battery. Okay, so I had 12 energies per charge. Each electron was carrying 12 units of energy because that's what 12 volts mean over here. They gave away some of that energy, 2 volts of it, to resistor A. 2 volts were given away here. I've got 10 volts left per electron. Each electron is now carrying 10 volts in that, or 10 units of energy in this wire right over here. If I measure the voltage across resistor B, I would find that I get 4 volts, 4 units of energy per electron, per charge, are lost over that resistor B. And that leaves me with 6 left. Remember that electrons are not allowed to have any energies left in their hands when they get back to the battery. So this last wire better be at 0 volts. If I have 6 volts left in this wire, because I had 12, I spent 2, I spent 4, I have 6 volts left in this wire, then if I measure the voltage across this last resistor, resistor C, those electrons better be giving away the last of those 6 volts. Okay, so voltage is not equal across components in a series circuit. Voltage is not equal. Each of those components could be using up a different amount of energy, but the total, if I add up the total, it better add up to my battery voltage. Okay, so let's see if we can apply these same 3 steps finding total resistance, finding total current, and then finding the voltage drop across each component to a new circuit. So here's a blank circuit. And what I'd like you to do is copy this circuit diagram into your notes. You have a battery and 3 resistors. And let's give these some values. We'll say that this battery is a 24 volt battery. My first resistor, resistor A, has a resistance of 6 ohms. Resistor B over here has a resistance of 2 ohms. And resistor C over here has a resistance of, we'll make it 4 ohms. Okay, your task is to pause the video, find total resistance, total current, and the voltage drop across each resistor using our 3-step method. Alright, let's try this out. So we have our circuit diagram. This counts as our knowns because I've drawn a diagram and I've listed what I know about the situation on that diagram with numbers and units and variables. So this counts as my knowns. I need to find the total resistance, total current, and the voltage drop across each resistor. Okay, let's write down Ohm's law so that we have it for reference. The current is proportional to the velocity and inversely proportional to the resistance. I equals V over R. My first step is to find the total resistance. So total resistance equals RA plus RB plus RC. RA we said was 6 ohms. So this is 6 plus 2 plus 4. And this time I'm going to have a total resistance of 12 ohms. First step. Second step, let's find the total current using Ohm's law. So I equals the total voltage over the total resistance. And my total voltage in this case is the battery voltage, which is 24 volts. So 24 over my total voltage, which is 12. Once again, we get 2 amps. Okay, the current is not always going to be 2 amps, but it just so happens in the 2 examples that I made that we had 2 amps flowing through the circuit. Okay, it could end up being any number, just whatever the total voltage of the circuit is divided by the total resistance. Okay, last step is we need to figure out what are the voltage drops across each individual resistor. And we can do that by applying Ohm's law to each resistor. We are zooming in on one resistor at a time. First, let's zoom in just on resistor A of 6 ohms. I equals V over R. So I know the current through resistor A, it's 2. I don't know the voltage, but I do know its resistance, 6 ohms. The voltage across resistor A is 12 volts. I'm just moving the 6 to the other side by multiplying both sides by 6. Same thing over here, Ohm's law applied to resistor B. Resistor B is 2 ohms of resistance. So what we're doing is we're zooming in on this resistor, this component. So let's zoom in there. I know the current through a series circuit is always going to be equal to the total current because there's only one path for electricity to flow. We're looking for the voltage drop across component B, and we know its resistance is 2 ohms. Let's move the 2 to the other side. 2 times 2 is 4. 4 volts. And finally, resistor C, up here at 4 ohms. We're going to zoom in just over there I know its current is 2, looking for the voltage drop across resistor C, and I know its resistance is 4 ohms. Moving that 4 to the other side, we get a voltage drop of 8 volts across resistor C. So once again, I can do a quick check to make sure that I'm right. If I add these voltages up, they had better equal the total amount of energy per charge that I have, which is 24 volts. Voltage is energy per charge. So let's add these all up. 12 plus 4 is 16. 16 plus 8 is in fact 24. So V total is 24 volts. Adding those up, and certainly that equals my battery voltage. So I know that I did that right. So it seems like a lot of steps for one problem, but again, it's really only 3 steps. And again, think about what is physically happening in the circuit as electrons are moving around. Think back to the electron shuffle. Voltage represents how many units of energy does each electron have, or does each charge have, as it walks around the circuit. Some of that energy is given away. In a resistor, it's usually given off as heat. But it could be anything else. We could be transferring that energy out of the circuit to use it in a cell phone display. We could be using it to move a speaker. We could be using it to turn a fan. Anything could be happening in any of these resistors, and what we're doing is we're taking energy out of the circuit, which is why they use up some of the voltage. Okay, and I add up the total energy per charge that's going out through each of these resistors, and I should end up with the total energy per charge that the battery is giving them in the first place, which is 24 for this circuit. Okay, pretty straightforward. Follow the steps. And once you get in the habit of following these steps, you'll start to be able to solve other problems involving series circuits that don't quite go in the exact same order, but use the same physics knowledge. So let's think about our objectives. Can you identify a series circuit based on how the components are connected in a circuit? Remember, we said a series means that one thing comes after another. So in a series circuit, one component of the circuit comes after another. They're all in a row, and there's only one path for electricity to take. And our second objective, can you apply Ohm's law to series circuits? Notice that in every series circuit, we applied Ohm's law multiple times. We did Ohm's law first with the whole circuit. We used the total voltage and the total resistance to find the current through the circuit. That's one time we used Ohm's law. Then we zoomed in on individual components and used Ohm's law again for each individual component. So we could be using Ohm's law many times to solve different parts of a circuit. It kind of depends on what we're looking at the moment and what is it that we need to solve right in front of us. And that's series circuits.